Section 1A is titled Higher Order Derivatives. I'm thinking we'd already done some of Section 1A. Is that accurate? Okay. We had talked the other day about the idea that drop a rock and you can determine heights by how long it takes it to drop. We had talked about the fact that there's this equation, S of t equals a negative 16t squared plus v sub 0 t plus s sub 0. What's v sub 0? The initial velocity, and s sub 0 is the initial height. Okay. If you take the derivative of this, okay, so this gives you height. Remember, derivatives describe how is something changing. If you take the derivative of this equation, it's going to tell you how is the height changing. Okay? And if you're looking at how the height is changing, let's talk about a couple of heights. Let's say you have some data, time and height. At 0 seconds, it's 6 feet. At 1 second, it's 30 feet. At 2 seconds, it's, say, 48 feet. At 3 seconds, it's, let's say 55 feet. Just kind of making some numbers up there. If you take a look at the average rate of change, okay, for example, between 0 and 2, what you're going to wind up with is 48 feet over 2 seconds minus 6 feet over 0 seconds. This is going to give you 42 feet per 2 seconds, which is going to give you 21. And what I'm really after here is the units. The units are in terms of feet per second. Feet per second describes what? It's a velocity, isn't it? Just like miles per hour is a velocity. Okay. This average rate of change is described by the first derivative. So this is one way to kind of back into the fact that the derivative in this case is going to describe velocity. Okay. And this is going to be a negative 32 t plus v sub 0. The next thing that we could look at is taking the second derivative. The second derivative, notationally, courtesy Leibniz, is going to be that, and it's going to be a negative 32. Does anybody recognize that number, negative 32 or 32? Or in metric it'd be 9.8. What is that? That's acceleration due to gravity, isn't it? Now notice the first word in that, acceleration. What the second derivative does here is it talks about acceleration. Acceleration is really talking about how the velocity is changing, isn't it? So realize the second derivative talks about how the first derivative changes. If the first derivative is changed, that means the velocity is changing. And as velocity changes, the measure of how it's changing is acceleration. The negative 32 is feet per second. Where that comes into play, or how those units come about, is when you're doing the average rate of change there, we could set up a similar table where we have our time, and here we would have velocity. Our time would be in terms of seconds, and velocities would be measured in terms of feet per second, wouldn't they? So this average here is going to be the velocities, which is feet per second, divided by the time, which is seconds. And do you see that that gives you feet per second divided by seconds? Which gives you a unit that, if you've had some physics or something like that, you've seen some strange things like that before. But if you've not had any physics, this may be the first time you've ever seen anything like feet per second per second. And what that means is, this last per second means that every second the acceleration changes by a negative 32 feet per second, or the velocity changes by a negative 32 feet per second. What's the negative mean on that? It's moving in a downward direction. So the negative just tells you direction that things are moving. Okay? So acceleration is the result of taking a derivative of velocity, and derivative of velocity, or the derivative of height, gives you the velocity. A velocity is the result of the derivative of the height. These higher order derivatives are important. They allow us to see what's going on. Now the good news is, in this year's calculus, you're only going to use first and second derivatives. We're not going to go into anything higher than that. Are there third, fourth, fifth order? Yes. Do they really mean something? Yes, they do. They mean all kinds of stuff, especially in things like physics and engineering and applications. Okay? But we're going to just stick to these three derivatives. When we're taking a derivative of something, let's say we have something like profit. P of Q equals some mess. What's the variable going to be in this equation? Q. Q is going to be the number of units, the quantity. Okay, it won't be at all unusual to be using Q as the variable because it'll refer to a quantity of some item being made. If we take the derivative of this, P prime of Q, and I'm going to change Q to some number like 12. And we figure out that P prime of 12 equals, and I'm making this up. Okay, so these numbers that are going to be appearing here, I'm just making them up. It's 27.64. What this is talking about is, well, what's the derivative of profit? It talks about how the profit's changing, doesn't it? Anybody had any economics classes where you study change in profit or change in cost or change in revenue? There's a word for that. Confusing, Chuck. It was really confusing. Okay? Well, the other word for it is marginal. What marginal profit literally means, or refers to, and the reason I'm writing this down like this without equations is I don't want the equations to confuse you right now. I want you to focus on the notation and just understand the notation. What this is really saying is, if we increase production from 12 units to 13 units, the profit will increase or we can say the profit on the 13th unit will be 27.64. Now, depending on the scenario, this could just be dollars. This could be hundreds of dollars, thousands of dollars, $1,000,000, whatever it might be. But there are several things I want to point out here. First, when we're computing a marginal profit, for example, I asked you, what would be the profit on the 13th unit? Well, to look at the profit on the 13th unit, we have to start at the 12th and move in the direction of the 13th, don't we? Does that make sense to everybody? So what we're going to do is we'll evaluate the marginal profit at 12. Because if we're looking at going to a 13th, where are we now? We're at 12, aren't we? Does that make sense to everybody? So be careful. If you are asked what is the marginal profit to make a 13th unit, you want to plug 12 in. Because are we for sure making the 13th unit? No, we're just looking at it. And remember, this is a slope. See that 2764? That's a fraction. It's over 1. And the way we would get that would be the profit at 13 over 13 minus the profit at 12 over 12. So you see the denominator really is there. There really is a 1 there in the denominator. Okay? And this fraction there and the 2764 are trying to tell you the same thing. How much additional profit will you make by producing a 13th unit? Okay, so the first thing to be really careful of, and this trips up a ton of people every year. This is why I'm camping out on this for a few minutes. If you want to know the marginal profit at the 13th unit, you plug 12 into the marginal profit equation. Because if you plug in 12, it's going to tell you by taking one additional step, see the 1 there? You're going to make this much more money. Okay? If you were asked, what is the profit to manufacture a 46th unit? The profit achieved by manufacturing a 46th unit. How would you compute that? What would you do to compute the profit on a 46th unit? Well, we're looking at moving from 45 to 46. So what we would do is we would evaluate the marginal profit at 45, and suppose it comes up negative 7.31. What's that tell you? No profit. Even worse than no profit, it's a loss. If we go from making 45 of these things to making a 46th unit, this extra unit is going to result in the loss of that much money. Well, how could you lose money by making more? Does that ever happen in business? Yes, it does. Well, how do you lose money by making more of them? I thought if you make more, you're doing better, aren't you? Not always. This is why you want to do the analysis. The making more may require you to hire extra people. That's money. May require additional equipment. That's money. May require buying additional resources that aren't in your contract right now, and you may have to pay a premium price for those additional resources. Okay? So you've always got to make sure that if you're looking at expansion, the expansion is going to be a profitable thing. Expansion is not always profitable. Want to see a classic example in the city of Cincinnati? Did you hear what they're doing down with Hilltop Concrete? No. Hilltop Concrete's down by the river. Well, the city has decided that they would like to take a piece of that property that's currently Hilltop Concrete and turn it into a parking lot for the Bengals to use for tailgate parties. Okay. But I mean, Hilltop Concrete's got to move, don't they? I mean, you can't have the parking lot there, tailgating, and a concrete company all there at the same time. So what the city's looking at doing, and I think they've already approved it, is to go ahead and buy a chunk of Hilltop Concrete. And what you know what Hilltop Concrete has said? Well, we need the land. We can't function without it, so we're going to move across the river. They'll still be close to Cincinnati, can get here, can still service their current clients, But where is across the river? That's still Cincinnati, isn't it? No, it's still Ohio, isn't it? What's on the other side of the river from Cincinnati? Kentucky, isn't it? So what the city is looking at doing is to buy out the property from a business and force that business to move to northern Kentucky. And in the process of putting in a parking lot, how many home games are there a year for the Cincinnati Bengals? Maybe 8? So how many days a year will that parking lot get used? 8? That's right. Okay? So what they're looking at doing, because that property is going to be under the control of the Bengals, they're running a business out of the city and out of the state into northern Kentucky so that they can open up a parking lot. It hasn't been disclosed who gets the revenues from the parking lot, either the city or the Bengals, one or the other, but it's sure not going to be free to park there. Which do you figure is going to make more money? A parking lot that you use 8 days a year, or a concrete company with 70 employees who are all paying taxes and the company's paying taxes 6 days a week? City's losing money on that deal big time, aren't they? Okay. So it's possible by expanding or improving, you're going to lose. City's going to be a loser on that deal. Okay. Does that make sense? Okay. Let's see here. Let's take a look at something like this. Ever hear of an iPad? No, Chuck, never heard of an iPad. Okay. Number of iPads sold. T years since 2010 is approximated by n of t equals 0.106 t to the fourth minus 1.452 t cubed plus 5.659 t squared plus 1.946 t plus 20.714. How many of you live in the Cincinnati area? Does that decision to buy Hilltop affect you and your parents? No, not really. It does, because you know all the tax base that was lost there, they got to get that money from somewhere. Where are they going to get it? Not from 8 days of parking fees. Okay? Okay, so what does this mean? Number of iPads sold 2 years since 2010 is that. How'd they get that equation anyway? threw some numbers down, and there they are. You plot the data, and remember in review section 7, we talked about doing regression analysis. We could have gotten this equation. All I would have had to do is throw the data up there and say, okay, plot the data. What type of an equation will fit that data? And we could have tinkered around with quadratic, a cubic, a quartic, and see what really fits best. A quartic would have fit best. Would have taken an extra 10 or 15 minutes, which would have ran us out of time in class. So instead of throwing the data up there and you figuring out this equation, which you could have done very easily, there it is. Okay. A couple of questions. One, how many iPads sold in 2017? This number sold is in terms of millions. So whatever we get out, if we get out 5, it would be 5 million, not 5 iPads sold. Because we all know that's wrong. Okay? So how do you handle something like this? What I would encourage you to do is to go to y equals, and in y1, put y1 equals, and put this number in. Well, why is that? Because what we're going to have to compute here is the value of this function at 7, aren't we? You could plug in 7 in those various places where t is. Okay. And you're going to have to punch in all the numbers anyway. And you have to punch in just as many numbers to enter the equation in once as to enter it into y equals. Several advantages to putting in the y1 equals. First, are you as likely to make a mistake evaluating the function? Okay? If you plug in the 7, you're more likely to make a mistake than if you plug it into y1. Yeah, but if I plug it into y1, how am I going to get a value out? You then go to the table and plug in x equals 7, and boom, there's the answer. And the cool thing is, suppose the next question says, well, how many were sold in 2018? Well, now you got to do is plug in 8, and boom, there's the answer. Either way, it protects against making mistakes. If you realize you've made a mistake, it's very easy to go back and edit this equation that's in y1 as opposed to typing in the whole thing all over again. Okay? How many iPads sold in 2017? Well, if you plug that in, what do you wind up with? What's that number, 68.097, mean? Well, remember, n, this function, is the number of iPads sold, isn't it? Okay. So this would be this many million iPads sold. If you were asked how many iPads sold in 2017, a good response would be converting it back to a number that actually reflects that we're talking about millions of units. Because one of the things you need to be mindful of is not everybody whom you're going to be working with once you graduate is as skilled in math as you are. I mean, you can look at that and say, well, sure, 68 million. I know what that looks like. There's some people who have no idea how many zeros a million is. And they may be right behind you on the expressway. Okay? You don't have to look hard to find them. So, a good thing to become accustomed to doing is to, when you report numbers, actually clean it up. So it isn't in terms of millions. 68 million, and write the number out with the commas and the zeros and everything else it takes. Okay. Question number 2. If you take the derivative of this function, now is the derivative of that difficult to do? It takes a little time, but what's to it? There's not much there at all, is there, to computing the derivative of that? Okay. What I would encourage you to do when you take the derivative of this, it's going to be 0.424 t cubed minus 4.356 t squared. I think I did that right. Plus 11.328 t plus 1.946. I think I did the multiplication right, was just doing it on the fly. There's the derivative. What I would encourage you to do, and to get in the habit of doing, is to plug this into y2. Personally, I always put the original function into y1. I always put the derivative into y2. And guess what I always put into y3? The second derivative. And it makes it very easy then, because when I go to the table function, remember on that table function it's set up to look like x, and it'll say y1, y2, and then you've got to move over, and it'll also show you y3. Okay, you'll have a table set up, but when I plug in the 7, it's going to give me the 68.097, and then when I plug in the derivative, what it's going to wind up giving me there is 13.16, and when I plug in the second derivative, it's going to give 12.662. And I'm going to have all kinds of information about sales in 2017. Getting the numbers isn't the hard part. What's the hard part? Explaining what they mean, right? I mean, I can say 13.16. That's pretty easy. Everybody's, yeah, 13.16 what? What these numbers mean, and remember, y1 is going to be n of t, y2 is going to be n prime of t, and y3 is going to be n double prime of t. Okay, keep in mind, that's what's going on, that's what you're dealing with. If we graph this function, okay, if we graph this function, the function sort of goes like this. With 7 being somewhere right around here. Okay, so the point we are on this graph is right around there. With the information that you have here, do you see that y1 has this value of 68? What does that mean on the graph? Well, that's the value of the function. That comes over to here to this y value here. Okay, so if I extend the y-axis up a bit, this is this value 68.097. Does that make sense what the y1 value it's kicking back is? It's just the y value, it's how many sold. y2 is talking about the derivative, and derivatives are always, begins with an S, slopes. Way to go, Jake. Thank you. Okay, derivatives are slopes. What the second value in that table is talking about is the slope of this tangent line. Now, from Apple's point of view, they don't care that it's a slope, other than the fact that 13.16, well, first off, that's 13,160,000. That's a whole lot of iPads, isn't it? You know what that's telling us? From the year 2017 to the year 2018, we can project selling an additional 13,160,000 iPads than what we sold last year. It's going to go up by that much. That's an estimate. Why do you need to have some idea of what's going to happen in sales for next year? Well, that's right, so you can make enough of them, so that you're sure that you have enough production capacity to meet the demand next year. Because if you do not have that iPad out there next year, do you think people are going to wait till 2019 to buy their iPad? All right, so I had the money saved up and I wanted to buy one here in February. I guess I'll wait till next January and see what happens. Think that's really going to happen? No, what are they going to do? They'll buy somebody else's, won't they? A very true statement in business is, if you do not take care of your customers, somebody else will. Okay? September 11, 2001. What happened? How would I know, Chuck? That was 18 years ago. I was too young to remember anything. Yeah, but think back. September 11th. What month is September? Number-wise. Oh, wait a minute. That's 9/11, isn't it? Oh, now I get it. Okay, September 11th. Oh, that's where the 9 comes from in 9/11. Okay? Yeah. John Deere forecast that the sales in tractors would be down the next year, so they made less tractors. 2010, I needed a tractor. Not a little one that you buy at Lowe's, I mean a tractor. Back tires are about this big, and that's my small tractor. Okay? I went to buy it, and they said, well, we can get you one. I said, great, how long? About 8 months. I said, dude, season's going to be over. Everything will have needed to be planted, harvested, and rolled into the barn before I get this tractor. That's too late. What's the deal? He said, well, they forecast there would be less sales this year because of 9/11 last year, and we found out we were wrong. So now we're 9 months behind on production. Well, could I wait 9 months to buy a tractor? I needed that thing now, not next year. I bought New Holland. And every time I've gone back to buy an additional tractor, guess what I buy now? New Holland. Found out they're less expensive. They're a great tractor. Ta-da. And John Deere did not lose one sale. They have now lost multiple sales just from me by a bad forecast. These things are worth a lot of money to be accurate. Okay? They are estimating that in 2018, total sales should be about, well, we're going to sell the 68,970,000 we sold the year before, and our sales are going to go up by how much? Well, they're going to go up by this much. This 13,160,000. So, in 2018, we better have production capacity lined up to make. Okay, we're going to have an 81 there. We're going to have, this looks pretty easy, 257,000. We need to have production capacity for over 81 million iPads. Now, here comes a very important next question. Is this estimate right on, high, or low? It's low. You're right. How'd you get that? Well, I had a 1 in 3 chance. Prince is right. It's low. Take a look at where 2018 is going to be on this. It's over here, isn't it? Now remember, when you do the derivative, you're doing a slope, and the slope's for a line. So when we're doing our estimates are based on this line. In 2018, is the estimate that line above or below the actual sales? It's way below it, isn't it? Well, Doger, so we got to have production capacity for well beyond 81 million. There's one teeny problem here. If we're in 2017, do we know exactly how many we're going to sell in 2018? No. So that part of the graph isn't there yet. Oh, bummer. What we have is this to look at. And there you are, trying to make decisions for next year, and that's all the data you have. It ends there. And you got to figure out what's going to happen next year. Well, the way that you figure that out is you look at the second derivative. The second derivative here talks about concavity. Remember we talked about this last time? To figure out if things are maximums or minimums. And what that tells us is at 2017, the graph is concave up. Concave up is going to behave like that, isn't it? I put it in dotted lines because we're living in 2017 and we haven't lived that time frame yet. We're guessing. But what the second derivative tells us is concave up, sales are going to continue to go up at an increasing rate. Does that make sense? Which means that our actual graph is going to be up here above our estimate. And that is killer important to know. If the second derivative is concave up, this tells us that the estimate using the first derivative will be low. Does that make sense why it's going to give you a low estimate? Really important to know. Now, if it can be concave up, it can also be what? Well, I guess it can be concave down. Let's think about what concave down would look like. Concave down is going to do something like that, isn't it? That's concave down. When you do the tangent line at some point, you're going to do something like this. Then, when you make your projection for the next year, you're projecting you're going to be up here, when in reality you are there. If it is concave down, our estimate is going to be too high. The estimate based on n prime of t will be too high. Does that make sense to everybody? This stuff is really important. because not only do you need to get an estimate, that'll come from the first derivative, but you then need to have some understanding about the direction in which this estimate is skewed. Is it too high or too low? Clearly there are times where you want to estimate too high, and there are times where you want to estimate too low. If I invite everybody over for a picnic this Saturday, do I want to over or underestimate the number of hamburgers that we need? Yeah. Okay. Definitely want more than enough there, right? As opposed to, geez, somebody call Domino's. Let's get a couple of pizzas. Em and Hacker ran out of food already. Okay. That's not much of a party, is it? There are times that you want to overestimate what's going to happen. There are times that you want to underestimate. And you've got to know what the number you're working with is. Yeah.
So did John Deere just underestimate based on like what was currently happening?
Yeah.
Okay.
And they
could have followed the whole equation, but then just gone with an underestimate instead of an over one, and that's what caused it.
Well, what happened was 9/11 wasn't the normal type of thing going on. So they had to guess, how's this going to affect the whole economy?
So at that point it was just like a 50-50 chance?
It was a guess. It was a guess. They were guessing that next year the economy would be down, there wouldn't be as much construction, farming wouldn't be buying as much equipment, blah, blah, blah. And they guessed wrong, and it cost them a lot.
What would it have cost them if they produced too many, though?
Yeah, if you produce too many, what's that cost you? Cost you money of all those tractors. Do they eventually sell them? Yeah. Like cars. I don't know if you've ever gone on a car lot, but it's 2019. There's still some brand new 2018 sitting around. Brand new. 10 miles on them. They overestimated how many they were going to be able to sell at that dealership. Will that car eventually sell, or is it going to stay there forever? It'll sell. And they'll recoup some of their money, but that's not one of the brighter spots in the company's history. Yeah, it gets tricky. If you make too little, you lose customers. If you make too much, there you sit. Whoa, this is kind of an important game, isn't it? Does it make sense to you what's going on with this? Okay. This is real important. We are going to be using this all year long. I know I keep saying that. I don't want you to feel like I'm just piling on one thing after another we're going to use all year long, but this is stuff we're going to be using. This is really important. The second derivative is going to tell us if our estimate is an overestimate or an underestimate, and that's an important thing to know. Okay? Everybody good with that? All right. So, in this section, basically we've talked about the fact that you can do second, third, fourth, fifth derivatives. We're going to stop at second order derivatives, which is just applying the rules of derivatives to whatever the function is that you already have. Okay. Second derivatives talk about how the slope is changing. How the slope is changing describes concavity. Is it concave down? Is it concave up? Concave down. Concave down means that the second derivative would be what relative to 0? Greater than or less than 0? Gosh, Chuck, I don't know. How am I supposed to remember that? Concave down looks like this, doesn't it? And this is literally the way I figure it out. Is that a smile or a frown? That's a frown. Are things going positive when you're frowning? No, things are going... Oh, so it's going to be less than 0. That's kind of stupid. I know it, but I remember it. Concave up. Second derivative is something or other. Well, concave up looks like that. What's that look like, a smile or a frown? Smile. And smiles are the result of things going positive. Now, the thing you got to be careful of is with concave down, you're at a maximum point. And with concave up, you're at a minimum point. So don't let that throw you off. Because sometimes people will see the positive and they'll think positive, ooh, that's good, a maximum. Wrong. Positive, smiling, a minimum. Okay, don't let that trip you up. Does that make sense to everybody? Okay. Okay, section 2.1 gets into exponential functions and logs and all that good stuff. We're going to get the formula for PERT and make sure that those are all running for you. I don't think 2 or 3 minutes is really enough time to dive into that. Wow, he's letting us out early? Yeah, like, what, 2 minutes early? Okay. Hey, I hope you have a very productive Thursday, Friday, Saturday, Sunday, and I sure look forward to seeing you on Monday. Take care.